All right, hey everyone, let's just jump right into it. Welcome to today's explainer. As tech leads and devs, we all know that sinking feeling when a model in production makes a wildly weird call and we're the ones on the hook for it, right? So today we're literally ripping open the black box. We're going to figure out how to debug these things so we can actually build reliable, secure, and most importantly, auditable machine learning pipelines.
Because look, here's the reality of the situation. Hitting 95% accuracy on a test set, it basically means nothing if the system's underlying reasoning is completely opaque. I mean, we might be high-fiving over a great metric, but if the model is secretly just piggybacking on some hidden bias or a totally spurious correlation, well, we've just built a fragile system that's going to snap the second it hits the real world.
Which leads us to the absolute biggest headache for our engineering pods. How in the world do we debug something we can't even see? When a deep learning model is burying its logic inside millions or billions of weights and parameters, how do we spot feature leakage? How do we catch algorithmic bias before it causes a massive disaster?
So here's our sprint agenda for this explainer. We're going to start by unpacking the black box dilemma. Then we'll map out how to trace those nasty bugs and pipeline biases. After that, we'll open up the XAI debugging toolkit, get real about what actually survives in production, and wrap up by navigating this huge clash between transparency and security. Let's get into it.
Okay, part 1. The black box dilemma.
Guys, take a hard look at this date, August 2026. This is the EU AI Act compliance deadline. And it means explainability is officially off the nice-to-have backlog. It is now a hard, legal mandate for high-risk systems. We literally have to be able to provide reconstructible, auditable reasoning for our automated decisions. If we can't do that by August 2026, we don't ship, period.
And honestly, that's exactly why explainable AI, or XAI, has to become a core part of our debugging stack. We need it to catch hidden proxies, like when a model secretly uses a zip code as a proxy for race. We need it to find the root cause when a model totally bombs on a specific user segment. At the end of the day, it's about proving our system works for the right reasons, building actual stakeholder trust beyond just waving around a raw accuracy metric.
Moving on to part 2, tracing bugs and pipeline bias.
Now, algorithmic bias is not just some random glitch, it is a systematic failure, and it sneaks in through a few main doors. You've got historical bias, where our training data just reflects past inequalities, like redlining in loans. Then there's representation bias, where we just undersample certain groups, leading to stuff like facial analysis gaps. And the worst one? Feedback loop bias. That's where a model's biased output, like in predictive policing, actually corrupts the future data we use to train the next iteration. It's a total nightmare.
So how do we fight it? We've got a 3-part mitigation playbook here: pre-processing, in-processing, and post-processing. Pre-processing cleans the dataset up front, but it totally fails if the ground truth label itself is corrupted. In-processing tweaks the model during training, but it's super complex because you need deep access to the loss function. And post-processing fixes the outputs at inference, but using different thresholds for different groups can open up a whole new can of legal compliance worms. Every single option has a serious trade-off.
All right, part 3. Let's talk about the actual tools, the XAI debugging toolkit.
First up is Lime. Now, Lime is awesome for rapid prototyping. It essentially pokes the black box, perturbing the inputs just to see how the model wiggles locally, and then fits a simple linear surrogate model to that little neighborhood. But here's the catch. Because it relies on stochastic sampling, you could run it twice on the exact same prediction and get totally different answers. So yeah, it's fast, but it can be super unstable.
And that's exactly where SHAP comes in. SHAP fixes that stability issue by treating the prediction like a payout in a cooperative game. And your features are the players. Because it's rooted in game theory, it gives you mathematically guaranteed efficiency and symmetry. It calculates the exact fair marginal contribution of every single feature. No guessing.
Put them head to head, and the contrast is pretty stark. SHAP gives you this unmatched game-theoretic exactness that is globally and locally consistent. But man, it is computationally heavy. You basically have to use variants like tree SHAP for it to be viable at scale. Lime, on the other hand, is model agnostic, it's fast, and it's great for quick sanity checks, but that local linear approximation is highly unstable between runs. The TLDR? Use Lime for a quick gut check, but trust SHAP for your actual compliance audits.
But hey, what if we're dealing with deep neural networks? For those, we pivot to integrated gradients, or IG. IG tracks how a prediction shifts as the input changes along a straight path from a neutral baseline, like an all-zero vector, to your actual input.
By integrating the model's gradients along that path, it satisfies this crucial mathematical axiom called completeness. Basically, it guarantees it accounts for 100% of the prediction's difference from the baseline. Very cool stuff.
Okay, part 4, production reality. What actually works when the rubber hits the road?
Look, we've all been there, staring at a dashboard at 2 a.m., losing our minds because an explanation keeps changing. The reality check is harsh. Lime's instability completely destroys operational trust. Exact SHAP, just way too slow for production. You absolutely need tree SHAP for scale. And those raw gradient methods, they often just amplify noise and saturation in deep networks.
If you want to see how this is actually done at scale, look at Uber's Michelangelo platform. They didn't just install a library and call it a day. They had to save their raw differentiable models, alongside the metadata, build custom model wrappers to standardize inputs, and even register gradient hooks deep inside intermediate embedding layers just to handle non-differentiable categorical features. They really had to get under the hood.
But the payoff for that architecture was massive. By bringing in the Ray framework for lightweight task parallel execution, Uber slashed their total attribution runtime by over 80%. 80%. And that right there proves the golden rule. If you want devs to actually adopt explainability, it cannot slow them down. Speed is literally everything.
Looking ahead, our toolkit is getting even smarter. We're moving from just asking, why did this fail, to how do we actually fix it? Using DICE, diverse counterfactual explanations, they give us actionable what-if fixes. And for the folks working with generative AI and LLMs, keep an eye on Token SHAP and DoShoply, which let us trace causality all the way down to the individual token level. Finally, part 5, transparency versus security trade-offs. This is where things get really tricky.
We are facing a massive architectural conflict. On one hand, the responsible AI mandate is screaming for transparency, open models, clear decision pathways, high compliance. But on the other hand, recent AMAS 2026 research proves that this transparency is a huge gift to attackers. Malicious actors are using our transparent explanations, or even just the knowledge that our model is defended, to craft highly effective, transferable adversarial attacks using surrogate models.
The numbers are wild. Researchers tested 9 different attacks across 181 models, and they found that our existing benchmarks have been drastically underestimating the threat. Transferable attacks against defended models can degrade accuracy up to 3.73 times more than we previously thought. And why? Simply because the attackers are adapting to our transparent defense strategies. It all comes down to decision dominance. In the cyber warfare game, it's all about establishing an information advantage on external uncertainties within a tiny, transient window. Whoever completes their information analysis cycle faster gains the upper hand. So, if we are completely transparent about how our defenses work, we are literally handing the attacker the exact info they need to match our strategy and steal the initiative. Which brings me to the final, provocative thought I want you all to take back to your pods today. We have always been taught that security through obscurity is a terrible engineering practice. But if an attacker matching our transparent defense strategy makes them nearly 4 times more successful, is keeping our model architecture and defense status obscure actually the most responsible choice for safety-critical systems? It's a tough one. Think about how you're going to balance that in your next sprint. Thanks for tuning into this explainer, team.